Okay, let's talk about ridge regression. So we're going to build up to this kind of slowly based on some of the methods that we've talked about so far with linear regression. But ridge regression basically is a more flexible approach to the linear regression model that we've talked about so far. And it's one that can be used in more settings, like we'll see today. Okay, so just as a refresher from what we learned about a little over a week ago, maybe 2 weeks ago, in linear regression, what is the thing that we're minimizing? And how can I write this in matrix form? So we're minimizing the residual sum of squares, which we can write like this. And so y minus x beta hat, that is our residual. And so if we want to take the residual sum of squares in matrix form, we can write this as y minus x beta hat transpose times y minus x beta hat. And what's the solution to this? Well, we solved this the other day in class. So beta hat is estimated as x transpose x inverse x transpose y. And we proved that that was true with the derivative. You basically walked through those steps in your application exercise. And those are going to be really important steps. Make sure that you kind of review them. Wink, wink, hint, hint, because it's going to kind of come up in the future on potential assessments to make sure that that's something you're familiar with, because we're going to be building on it for using ridge regression. So what is this X? It's a design matrix. And by design matrix, I mean it is a matrix where the first column contains all ones and the subsequent columns contain your predictor values. And how did we get that X transpose X inverse X transpose Y? Well, here are all of the steps laid out for you, but basically we came up with these equations by distributing those terms from the residual sum of squares, and we set it equal to 0. And then we rearranged the equation. We took the derivative, and we ended up we got to this by taking the derivative of this here. So we FOILed this equation. We took the derivative of it. We end up with this right here. Set that equal to 0. Rearranged. And ended up with this beta hat equals x transpose x inverse x transpose y. So if you remember this very first step, what we did to get here is we took the derivative of that residual sum of squares, and then we set that derivative equal to 0 because that's how we minimize something. And then we solved all of these equations down until we got to beta hat. Okay, so let's try to find an x for which it would be impossible to calculate a beta hat. And so let's talk about how we would calculate this in R. And so I'm going to build up to this, and then you're going to try to find an x for which it's impossible. So here I've got a little bit of data. We've got a single predictor x here. So we've got one predictor in this data frame. And of course, we've got one outcome y. And if I wanted to put this into R, I can put y in as a vector. So I'm using this C to concatenate these values, and so I'm doing 4, 3, 1, 3, 5, taking the values from my data frame and I'm putting them into a vector, and I'm assigning that to the object y. Similarly, I can make a design matrix in R by using the matrix function. And so what I've done here is I'm assigning this to x, and I'm using this matrix function. And the first argument of the matrix function are going to be the values. And so I am going to have those be 1 to 5. And then I'm going to have them, so this, this rep 1 5 times. And so what this does is it repeats the number 1 5 times. And the reason I want to do that is because there are 5 observations in my data frame, and I want my first column to be all ones. And so if this were a bigger if I was fitting a bigger data frame, like let's say there were 10 observations in this data frame, I would repeat or use rep of 1 10 times. And so that's going to be the number, we're going to repeat 1, the number of rows that there are in my data frame. And then the second argument here are just my x values. And so because I only have one set of x values, I just have one set here. So that 1, 2, 5, 1, 5. And then I'm going to set the number of columns to be 2. So this is how we make a matrix in R. And when I do this, I end up with this nice matrix where I've got all of ones at the beginning and I've got my x's afterwards. So this is my design matrix. I can take a transpose in R by using the T function. And so this is my normal matrix. my design matrix. This is the transpose of that. And you're probably guessing where this is building up to, because essentially what we're doing is we're building up to being able to calculate that beta hat in R. And so if I take X transpose, I can multiply matrices by using this percent and then the asterisk and then a percent. So this is how we do matrix multiplication. And I can multiply, so if I want to take X transpose times X, I would do it like this. I'll take the transpose of my design matrix, and then I'm going to do matrix multiplication and multiply it by X. And I'm saving this object as XTX. And because I want to take the inverse of it, I use the solve function. So the solve function in R is a way to be able to take an inverse of a matrix. Okay, so what have we done so far? We've created a vector for Y. We've created a design matrix for X. We've taken the transpose of X. We've multiplied that by something. We multiplied that in this case by X. We've learned how to take the inverse of a matrix by using the solve function. And so let's put this all together. We know that the equation for beta hat is X transpose X inverse X transpose Y. And so in R, we're going to do the transpose of X times X. And then we're going to wrap that whole thing in a solve function. So that's going to take the inverse of that first part. Then we're going to multiply that by transpose of X. And then we're going to multiply that by our vector Y. And so this gives us our beta hat estimates. So this is beta 0, beta hat 0, and this is beta hat 1 for my small data set with those five observations. So beta hat 0 is 3.5, beta hat 1 is negative 0.107. Okay, so what I want you to do is I want you to create a design matrix X, create a vector Y, make sure they're compatible. So what I mean by that is that if Y has 10 observations, then your design matrix X must have 10 rows. If Y has 3 observations, then your design matrix X must have 3 rows. So I want you to create a design matrix X and a vector Y, and I want you to use this equation, and I basically want you to break it. So I want you to find a matrix X for which it's not possible to create a beta hat. And so in particular, I want this to not work for something other than the dimensions of X and Y are not compatible. So do make sure that Y has the same number of elements as X has rows. But otherwise, use any kind of matrix X that you would like, as long as it's in the design matrix form, where the first column is ones and the subsequent columns can be whatever you would like for them to be. So I'm going to give you a couple minutes to try that. So I want you to fiddle with it and try to find something that breaks in R.